Today we will learn the use of pumping lemma for context-free languages. If you remember, we have already learned the use of pumping lemma for regular languages, and we could conclude that this language is not regular using pumping lemma, right? But we never decided that okay, using pumping lemma that this language is regular, but to test the non-regularity of a particular language we used pumping lemma there. So here what the theorem is saying that pumping lemma for context-free languages says that in any sufficiently long string in a CFL it is possible to find at most two short nearby substrings that we can pump in tandem. What it means, if you remember the case of regular language, we just divided the total string given to us into three parts, right? And the innermost part, or say the middle part, we pumped it several number of times and decided that whether the language is going to get accepted or not, and we proved that it is not regular, or we had never decided that it is regular, but it is not regular. We come to this kind of conclusion, right? So here, in place of finding out any one position or any one short position in the middle which we can pump, we will find out two different positions, right? How to do it we will see in our later slides. Right. We may repeat both of the strings I times for any integer I, and the resulting string will still be in the language, and this should be the outcome. Means whatever the two different small strings we are choosing, we have to pump it I number of times. I can be any integer, right? And whatever the resulting string will be generated after pumping, that should be in the language as well. We may contrast this theorem with the analogous pumping lemma for regular languages, which says we can always find one small string to pump. Right here we have already covered this point beforehand. In case of regular language, we find one small string instead of two. We all know. Say we are considering a language 0 to the power n, 1 to the power n. If you remember, we used this language 0 to the power n, 1 to the power n, where n is greater than or equals to 0, and proved that this is not a in case of using the pumping lemma, we proved that this is not a regular language. But here we will see that by fixing in and pumping a substring of zeros, we getting a string with more zeros than ones, and this was what we find there, and so we concluded that this is not regular. But here what we will do, here the CFL will pump that we can find two small strings, so we might be forced to use a string of zeros and a string of ones, thus generating only string in L when we pump, right? Here if you remember the previous one, if we had to pick up in between that 0 to the power n, 1 to the power n, so we picked up a string with fewer number of zeros and more number of ones. But here, since we have to pick from two different position, and you will see in the later slides how we are fixing two different positions, then it will be clear why we are saying that we might be forced to use a string of zeros and a string of ones. We will see there. So here maybe the strings might not be the combination of zeros and ones, but the situation may be like this, that one string is consisting of only number of zeros and other string is consisting of only number of ones, right? So here if we keep on pumping, no issue, but ultimately, so we will be fortunate enough and can come to the conclusion that this is in CFL, right? So in the previous case we were not fortunate and we could not conclude that this is a regular language. We have to come to the conclusion that fine, this is not a regular language. But here, since the approach is slightly different, so we can come to the conclusion that this is context-free language. So you might be eager to know that what is the actual procedure which we are going to follow, so that we can understand that what are the two different positions, how we are selecting two different strings, and so on. So let us before going to that one, we will see one more thing, and then we will directly proceed to that part. And here firstly we will focus on this part, because we have to learn one theorem and we have to prove it off. will later on, not in this lecture, but later on we may need this theorem for our purpose. Right, here what is our first step in deriving a pumping lemma for CFL is to examine the shape and size of the parse tree. We have learned what is a parse tree, so here we will focus on shape and size of the parse tree. How that this theorem is going to help us, we will see. So one of the uses of CNF, that is Chomsky normal form, we have covered that in just in the previous lecture. So here one of the use of CNF is to turn a parse tree into binary tree, but for the purpose of simplicity, if you want to learn how a CNF can turn a parse tree into a binary tree, you can follow any of the ebooks that I have shared in your group. But for the simplicity, we are not going to focus on that, how a parse tree is getting converted to binary tree, but we will just assume that this is true, not assuming, it has been proven to be true, so we will just pick it up and we will use it. We will not prove here, we will not show the procedure of converting a parse tree into binary tree. But if we follow the CNF, that is Chomsky normal form, if you can convert a grammar to a Chomsky normal form, then you can see that parse tree what we can draw in a grammar, and whatever the grammar we have generated in CNF, whatever tree we are drawing, that is ultimately a binary tree. This is the main thing, right? So these trees have some convenient properties, one of which we will exploit here. Let's see which property we are going to experience here. Right, so the theorem says, suppose we have a parse tree according to a Chomsky normal form of the grammar this, and suppose that the yield of the tree is a terminal of string w. If the length of the longest path is n, then we have the length of w can be maximum, this one, right? So this is a very very useful theorem. So if we can if we know the right, so we can just generate the number of if we know the long path of the tree, or the longest path of the tree, that is the value of n, we can say what can be the maximum length of the string that this tree is going to accept, or which string we can build using this parse tree, which string this grammar is going to accept and which string it is not going to accept, we can easily know here. So here what w is the length of the string, and the size of w can be maximum 2 to the power n minus 1. We know this is the property of the height of binary tree, so we are going to see it, how to prove this one. Firstly, we will go through the method of induction. So we know that method of induction begins with the basis assumption or basis solution. What basis assumption says, if the n means the longest path is n equals to 1, that is only one path, single path is there. So if you remember, the length of a path in a tree is the number of edges. That we know that how to calculate the length of a tree, we have to start from the root node, and the longest path, how many edges are there, we have to calculate. And another one is that whatever the number of vertices are lying, or number of nodes are lying, that should be one less than it, because always number of edges is one less than the number of vertices it is consisting of, right? So thus in case of tree, I am not talking of graph. In case of tree, it is, the fact is always true that whatever the number of edges are lying in that path, so the number of nodes will obviously be one less, right? And the edge will be one lesser than the number of nodes, right? So there's a tree with a maximum path length of 1, consisting of only a root and one leaf labeled by a terminal, string w in this terminal. So here what should be the length of the string, maximum length of the string? So if you follow the derivation pattern, that the production rules, so if we have to label this tree to a grammar, say if the height is 1, so it should start with a root node and end in a terminal or the leaf node, right? And it should have only one edges connected in between. So if we have to build this form of tree using the production rule, what should be the scenario? It should have a start variable and it should end at one terminal point, say s derives a, right? So this is only possible thing here. So here the length of string what can be the maximum value? Only it can derive a, right, in my example. so the length of the string is becoming 1. So it is following the property. Just see, if we put 1 in place of n, so 2 to the power n minus 1, if we substitute 1 in place of n, it is becoming 2 to the power 0, which is obviously 1. So it is true for the basis case. Now let us move for the cases where it is not following this basis pattern, where the length of the tree is greater than 1. So see, here we cannot consider any derivation like a s derives a. Now you will be here you may be surprised that why we are not using capital A is deriving another terminal capital B, and then capital B can derive anything in this form. But we have to remember, we have to follow Chomsky normal form, right? So Chomsky normal form supports this pattern. One variable can derive two variables at a time, so we have to follow this pattern. And so the root of the tree uses a production which must be in the form of a derives bc, and since n is greater than 1, so we cannot use two types of production rules are allowed here. One variable can derive two variable at a time, or one variable can derive a terminal at a time. So we cannot use the second one, because if we just incorporate this one variable is deriving a terminal, then the length will be restricted to 1 only, the length of the tree. So we have to use this one only. So no path in the subtrees rooted at B and C can have greater than n minus 1, obviously. So if total n nodes are there, so what can be the maximum length of the tree? So it should be n minus 1, right? Because the number of edges will be n minus 1 only. So this can be the maximum length of the path. So since these paths include the edge from the root to its child labeled B or C, so say we are starting from A, so we can, or say we are starting from any of the node, we can move to any child level, say there may be other productions. So to reach B we can maximum follow n minus 1 path, and again to reach C we can follow maximum of n minus 1 path. So we know that if we just concatenate these two, that it will become 2 to the power n minus 2. Why 1 lesser? Because we are already incorporating one path from the root itself, right? So here it will be 1 lesser. So in 2 to the power, what we will substitute, if you remember the equation, 2 to the power n minus 1, right? Original equation. So here in place of n, we have to substitute, since the length cannot be greater than n minus 1, as I have told, it has already incorporated the path from root to the next node, so it is n minus 1. So the value of n is becoming n minus 1. So at the place of n, we have to substitute n minus 1. So 2 to the power n minus 1 turns to be 2 to the power n minus 1, and that is n minus 2. So this is also true for C, right? So once for B, another for C. So if we can consider these two, it is becoming 2 to the power n minus 2 plus 2 to the power n minus 2, and it is coming to 2 to the power n minus 1. So it is true. Again, the theorem is true. So we have completed this part. Now we will directly move to the statement of pumping lemma, which we were talking since now, and then we will see some examples. Right. So the pumping lemma for CFL is quite similar to pumping lemma for regular languages, but here we break each string Z in CFL into 5 parts. If you remember, in case of regular language, we broke this into 3 parts and we pumped the middle part. Here what we will do, we will break the total string into 5 parts, and we will pump the second and fourth part, and we will keep on pumping it. Let us see how it looks if we focus on the theorem. See here, one L is a CFL, then say we are considering a constant n, such that if Z is any string in L, then the length of Z is at least n, right? And we can write, so what we told you, means what we have seen in the previous slide, that we will divide the total string into 5 parts, right? So what are the 5 parts we are considering here? U, V, W, X and Y, right? And here we will assume this, or we will follow these 3 constraints or 3 statements or conditions. What it says, the first point is the length of VWX. If you see the string divided part, that is Z equals to U, V, W, X and Y, the middle part V, W and X should be lesser than equals to N, and we have assumed the total size of z should be at least n, right? So we are assuming the middle part to be like this, and it is not too long, right? It is not it should always be lesser to n or equals to n. Now, since we are going to pump second and fourth part, what is the second part? V, and the fourth part is x. So this 2 should not be empty. We have to pump. There should be at least something with it, right? So it should not be empty. Now, for all I is any integer which is greater than equals to 0. Remember, greater than equals to 0. So we can even pump I. Means it can be 0, means 0 time we can even pump I 0 number of times. So 0 is also allowed. It is very similar to the case of regular languages what we have seen. So what should be the form? U v to the power I w x to the power I y. We have to prove that this is also in L or CFL. Then only we will say that the total language is in CFL, the pumping lemma for testing. If we can prove this is wrong, so the language will not be in CFL, right? Fine. So this is the statement. Now how we will move applications means that how we are going to use the pumping lemma for CFL. We have used in case of regular language, we have broken into 3 parts, pumped the middle element I number of times, and we could conclude that, oh no, we assume that this is in regular, and we have concluded that this is not regular, right? We have contradicted ourselves, or we have proved ourselves to be wrong. That was our approach. Here we will also follow the same one. So what we are going to do, we pick a language L, and we want to show it is not a CFL, right? So here the goal is also same. What was our objective in case of regular language? We picked up a language, and ultimately we wanted to prove that this is not regular. That was our job. So how we proceed? We first pick up a language and consider, no, we will consider, I'm saying that this is regular. Ultimately, what is my goal? I will prove myself wrong. So here we will do the same thing, right? So our adversary gets to pick n, which we do not know, that we therefore must plan for any possible n. So rather than discussing more here, we will directly move to the examples. I think it will be clear. So what we are going to do, we get to pick z, and we may use n as a parameter when we do so. We have already seen the theorem part or the statement part of pumping lemma for CFL, that we will pick up a z and we will use n as a parameter. Here we know that we are going to break z into 5 different parts, u, v, w, x and y. We will consider the middle part, that is v, w and x, to be not too long part, and it should be lesser than equals to n, where the total side of z is at least n, right? So this should be the scenario. And the which 2 part we are going to pump? We are going to pump v and x, and that should not be empty, right? Fine. So we shall now see some examples. First example shows while context-free languages can match 2 groups of symbols for equality or inequality, they cannot match 3 such groups. What it means, there is a trick to remember. Say in any competitive exam you are facing this kind of question, whether this language is context-free language or not. So if you just use your brain, that which kind of language can be context-free, right? So we discarded those languages as regular, where a concept of memory was there, right? Where we have to remember something, say 0 to the power n, 1 to the power n. To make this or to prove this regular, what we had to do, we have to remember the number of zeros we have visited. Then only we can compare the number of ones with the number of zeros we have visited. If these two are same, then we can conclude that this is regular, otherwise not, right? So there were no memory associated to regular language, and we could not help it out. But here we are having a memory, PDA, right, which we use, not PDA, it's stack, which push down automata uses to prove that this is a CFL. So what it is doing, it is going to say 0 to the power n, 1 to the power n. It will keep on pushing 0, 0, 0. When it comes to 1, it will keep on picking up or popping up 1, 0 at a time. If the stack becoming empty, and we have covered all the ones, so it is getting matched. It is okay, this language is going to accept or not. So this is a CFL. But if we have to do, instead of this 2 matching, if we have to do 3 matching, say 0 to the power n, 1 to the power n, 2 to the power n, so how can we remember? It can just push and can pop, right? So whenever we will see 1, we will just pop up zeros and nothing remains in the stack, and still 2 remains, the total 2 part remains. So this will obviously not CFL. So if you can find out any kind of language where 3 comparisons are there, more than 2 comparisons are required, that will definitely will not CFL, but still we need to prove it theoretically. So we will see how pumping lemma is doing it, right? So this example I was talking about here. So here, say we are having one language 0 to the power n, 1 to the power n, 2 to the power n, where n is greater than equals to 0. So here here considering still it is equals to 0, but fine, we are considering a string 0 to the power plus 1 plus and 2 plus, means the string, we are not considering empty string here. You may consider it, but still we are focusing on this kind of strings here. So there will be at least 1 0, at least 1 1, and at least 1 2. But please see the 3 variable, it is using the total, all the exponents of all the digits are same. So here number of zeros, number of ones, and number of twos are always equal. You cannot keep more number of zeros, lesser number of ones, more number of twos. This is not possible. So the choice of strings can be like this: 0 1 2, 0 0 1 1 2 2, or 0 0 0 1 1 1 2 2 2. Follow like this, right? So it should always have equal number of zeros, ones, and twos. Fine. So let us begin. So what is our how will we proceed? That we have to break z or the string into 5 parts: u, v, w, x, and y, and these are the same thing. I am not again talking of the same thing repeatedly, we have already seen it. Now then we know that v, w, x cannot involve both zeros and twos. Just see, it is very easy to understand. If we are saying that the total z is of at least of length n, right, and vwx are of means it can be lesser than n or equals to n, but the least length of z is n, right? So here, if this is the situation, then can you say that vwx can have both zeros and twos? It is not possible, because string is starting with 0 and string is ending with 2. So everything cannot be within vwx, right? Since the last 0 and the first 2 are separated by n plus 1 position, obviously, so the string will be like this: 0, then followed by 1s, and followed by 2s. So if you see the first, since the number of 0 should be n, number of 1 should be n, and number of 2 should be n. So if we start with the last 0 encountered in the string and with the first 2, so here how many n ones are there in between? N number of ones, right? And we are also incorporating the last 0, so n plus 1. So between last 0 and first 2 there are n plus 1 positions, and we are saying that vwx should be lesser than or equals to n. So how this is possible? If vwx has to have all that means it should have both zeros and twos in it, so this, then it is not satisfying the condition, because the minimum number of position gap between 0 and 2 should not minimum, it is a fixed one, because number of 1 should be n, and so the position gap between the last 0 and first 2 encountered is n plus 1, and it is not satisfying the criteria. Now let us see other assumptions. We will see some cases. Say if we are assuming the case 1 as vwx has no 2's, we are assuming, okay, fine, this is not the first choice, is not possible, then we are assuming this fact that vwx has no 2, so it is having no 2. Then vx consists of only zeros and ones. Why? Because this vwx, if it is having no 2's, then v and x should have only zeros and ones. Why we are discarding w? Because since we are going to pump v and x, it should not be empty. W can be anything. That's why we are considering only vx consists of only zeros and ones and has at least one of these symbols, right? Then u, w and y, other than this this your vx, we are remaining with this u, w and y, which would have to be in L by pumping lemma that it has n 2's but has fewer than zeros, n zeros or fewer than n ones or both, right? So if we have to consider this fact that vwx has no 2's, then the fact is coming to this, that v and x has only zeros and ones, and if this is the fact, then u, w and y have 2's, fine, n number of 2's, because we are not keeping any 2 with vx part, but it will have in lesser than n zeros and lesser than n ones or both. So it is not again belonging to CFL. This should not be the situation. And if you consider the other cases, VWX has no zeros. Similarly, whatever the choice you are making, it is having no zeros. Then it will have fewer number of zeros. Fewer number of ones or fewer number of twos in u, w and y, and if you follow the other part, one in between, not possible. So if we follow one case that there is no twos is present in vwx, it is not also contradicting, and again if we consider it is not having any zeros, again it is contradicting. So we can say that no, this is not a CFL. Fine. Second, what we are doing, we are considering another situation. See here what the language is saying: 0 to the power I, 1 to the power j, 2 to the power I, 3 to the power j. You can see here it is comparing 0 with 2 and 1 with 3. This is also not possible in case of CFL. We will proceed in the same manner. We are considering one variable, say constant, say n. We are raising all the power into the power of all the digits possible are present here. So we are breaking it into 5 parts, and now we will again follow the same pattern. Say this one, that say if vwx has two symbols, say the ones and twos, then u, w, y is missing either some ones or some twos. The same pattern we are following here as in case of the before. So we will consider that this small part, that is in the between part, is not having these two pairs. Again, if we follow in the other part, say suppose it is missing 1, as there are n 3's, this string cannot be in L, and if we follow the other part, then this is also not in L, right? So following the same pattern, so this is not also in CFL. So this, if this kind of situation comes where we need to compare 3 symbols or we have to compare alternative pair, these things are not possible to be CFL. So this again we are using the pumping lemma to prove that the language is not in CFL. Similarly, we have proved in case of regular languages. And so this much for today, and in the next class we are going to learn very important part, what are the properties of CFL. We will just see, there will be we will learn various properties of CFL, the closure properties, the membership properties and all. Okay, thank you.